All right, so to summarize our integrated rate laws, where we focus only on three, zero, first, and second order reactions, these are the rate laws for each of those. Now, the units for our rate constant K is different for each order of reaction. So let's derive what those units actually will be. So let's first look at a zero order reaction where our rate law is K times the concentration of A raised to the zeroth power. That concentration of A raised to the zeroth power is going to go to 1 because anything raised to the power of 0 is 1. So for a zero order reaction, our rate is equal to our rate constant. Now our units for rate is the change in concentration of our reactants or products over the change in time. In this case, we're talking about reactants. So our change in concentration we express as molarity, and I actually don't even need these brackets, right? I have M for molarity over the change in time, which is seconds. So the units for rate is molarity per second. And since our rate is equal to the rate constant, it turns out that our units for our rate constant is the same as our units for our rate, which is molarity per second. Now let's look at a first order reaction where our rate law is rate equals K times the concentration in A raised to the first power. This is a first order reaction rate law. So plugging in our units for our rate, molarity per second is equal to K. Our concentration of our reactant is expressed as molarity. So we just plug in molarity here. We solve for K. So if I divide both sides by molarity, I'm going to end up with K equals 1 over seconds. So our units for K is 1 over seconds. I'm going to let you work through how to derive the units for K for a second order reaction. But just to summarize it, this is what our units will be. So for a second order reaction, it's going to be 1 over molarity times seconds. All right, so let's look at a practice problem. So let's say this is our reaction, right, where it's some reactant X that interacts with some reactant Y that forms the product Z and Q. Now, it was experimentally determined, right? They determined that the rate law for this reaction is equal to K times X raised to the 0th power times Y raised to the 2nd power. So this reaction is a second order reaction overall, right? Because if we just add our exponents, it's 0 plus 2, which is 2. Our order with respect to reactant X is a 0 order, and our order with respect to reactant Y is 2. So the question asks, if the concentration of X is doubled and the concentration of Y is halved, what happens to the rate of the reaction? So since X is a 0 order, right, it doesn't matter how the concentration changes, right? Because it's always going to go, this term is always going to be reduced to 1. So in this case, we're looking at what basically happens when the concentration of Y is halved. So the way that I would solve this is I would just make up a number, right? Let's just say the concentration originally for Y, for reactant Y, was 4 molarity. Now, if it's halved, half of that is 2 molarity. So I'm going to solve for our rate in both cases, and then I'm going to compare the rate to actually answer the question. So when our concentration of Y is 4 molarity, our rate is going to be equal to K times 4 molarity squared. So if I solve this term, 4 squared is 16. We have molarity squared, because molarity times molarity is squared, times K. Now, when we halve this concentration of Y, the rate is 4 m squared times K. So if we compare these two numbers, we basically see that our rate decreases by a factor of 4. It decreases by a factor of 4.